Shit, I didn't realize you had a mustache now. All right. Okay. Okay. So now we'll do a quick recap and then we'll. So if you have square matrix, um, most matrices we can find vectors like right, and x of course is not equal to 0. How many can we find like this that satisfy this relationship for an n cross n matrix? We can find n. We can find n pairs like this. If it's a matrix that allows us to do this, there are some matrices for which we cannot do this, but for the good matrices you can always do this, right? And we found and we looked at the procedure for doing so. So how would you find the eigenvalues? So you always start with the eigenvalue. At least if you're doing by hand, you do this. Right. So we solve a polynomial equation that comes from taking the determinant of this matrix A minus lambda I, where lambda is your unknown, and the roots of that will be your eigenvalues. And then for each eigenvalue, you have to now go out and find the eigenvectors. How do you do that? The value for the lambda. Right. You choose any eigenvalue for which you want to find. You want to find the corresponding eigenvector, and those two will satisfy this relationship. A minus lambda I into identity matrix multiplied by the corresponding eigenvector will be 0. So essentially, you have to find a null space of this eigenvalue. And there's something we'll have to kind of remember. So if distinct eigenvalues, distinct lambda I, will have distinct or will have linearly independent xi. If you have two eigenvalues, lambda 1, lambda 2, that don't have the same value, then the corresponding eigenvectors will be linearly independent. Okay. Right? That means wherever you have a situation where the eigenvalue for an n cross n matrix, where the eigenvalues are different, right? Then for sure you can find n eigenvectors and n eigenvalues, n eigenvalues and n eigenvector. The problem comes when the eigenvalues are repeated. When they are repeated, we define two terms. Okay, one is called algebraic. Sounds complicated, but it's very simple. Algebraic complexity is simply the number of times the eigenvalue is repeated. Okay. For example, what are the eigenvalues of this matrix? So for diagonal matrix, it's very easy. It's simply the diagonal elements. It's got two eigenvalues. Both of them are the same. That means the eigenvalue 2 for this matrix has an algebraic multiplicity of 2. Okay. If I have 2, 0, 0, 1, then there are two eigenvalues. The algebraic multiplicity of the eigenvalue 2 is 1. The algebraic multiplicity of the eigenvalue 1 is 1. 1. Algebraic multiplicity. How many times is it repeated? 1. So that's the algebraic multiplicity. So, and it's the algebraic multiplicity of an eigenvalue associated with the matrix. So if you have distinct eigenvalues, n distinct eigenvalues, all the eigenvalues have an algebraic multiplicity of 1. Okay. Now, the next one is called the geometric eigenvalue. Okay. Let's say eigenvalue lambda I. Okay. So what you do here is you first you solve this equation. You take the eigenvalue, you solve for the null space of this A minus lambda I matrix. Okay, you will have a bunch of xi's that will give you this. Okay, now the span of all possible xi's that satisfy this equation. Okay, this will in fact form a subspace, right? The geometric multiplicity is simply the dimension of the subspace. Okay, we will take this as a definition for now, right? The set of xi's that solve this equation for this lambda I will actually form a subspace, and the dimension of the subspace is your geometric multiplicity. Okay, let's go back to some of the examples that we solved yesterday. Let's go to the first example. What is the first matrix for which we solved for the eigenvalue eigenvectors? Maybe it's 2 2 1 1 2 1 1 2. Yeah. Okay. Okay. What are the eigenvalues? 3 1. 3 1. Okay. So I'm going to write lambda. I'm going to write algebraic multiplicity, geometric multiplicity. Okay. What are eigenvalues? 3 1. What is the algebraic multiplicity of this eigenvalue? 1. It only appears once. This one. What about this? So go back to this equation that you solved for. Okay. For 3, what are all the possible xi's that actually satisfy this? What is the alpha alpha? That's vector of the form alpha alpha, right? So if you take or vector of the form 1 1, you can multiply it by alpha, and any such vector will solve this, right? That means the span of this one single vector will actually solve this equation, is a solution to this equation. And what is the dimension of this subspace? It's a span. The span of anything has to be a subspace. What is the dimension of this subspace? 1. Why is it 1? A number of elements, not the number of bases. Yes. This is a span of a single vector, right? That means if you simply choose this set, that will form a basis for this entire subspace. That means the basis has one element. That means the dimension of the set of the subspace that solves this equation is 1. Okay, this is in fact the eigenspace of 3. This eigenvalue 3. Okay, remember when you have an eigenpair, of course, if you take a xi, you will get lambda I xi. If I take any vector y that belongs to the span of xi and I stick it here, I will get lambda I y. For example, if I take 1 1 and I put here, I'll get 3 3. If I get 15 15 and I put it here, what will I get? What will I get? If I take the vector 15 15 and I multiply it with this matrix, maybe do it and tell me. Yeah, 45 45, that's 3 times 15 15, right? So if you take any element from the span of this, this is still satisfied. Okay, and the dimension of this subspace is 1 in this case. So the geometric multiplicity is 1. What about 1, 1? So what about lambda equals 1? What is the geometric multiplicity associated with the eigenvalue 1? Why is it 1? 1 is correct. Why is it 1? Hey, very simple. Hey, what is the eigenspace associated with 1? That means it's a subspace of vectors. If you choose any vector from that subspace and you multiply it with this matrix A, the vector that comes out will simply be a scaled version of the vector that you started with, and that scaling factor will simply be your lambda. Yeah.
Non-unique lambda values will get common.
Yes. Yeah, exactly. As long as your lambdas are unique, the associated eigenspace will always be a subspace of dimension 1. Okay, because there is only one vector. So if lambda is a unique, there is only one xi that will exactly solve this. In fact, you can show that there cannot be two different. If lambdas are unique, then there is only one vector. Okay, two different eigenvalues cannot have the same eigenvector. Okay? Eigenvalues are different, eigenvectors are different. But if the eigenvalues are the same, then it's a little complicated. Sometimes you can have a solution, sometimes you might not. So with that discussion, what is the geometric multiplicity of this? Why is it 1? You are correct. Why is it 1? Let's follow the same argument we applied here, right? What is the eigenvector associated with 1? Yes, this will solve it. This will satisfy ax equals x, right? That means this one will also satisfy. That means anything from the span will solve it. What is the dimension of this? 1. It's a one-dimensional subspace, so it's 1. What about the next matrix? What is the next one we did? Yeah. What are the eigenvalues? Oh, you don't have to look there. It's a diagonal matrix. What is algebraic multiplicity is 1, so no problem. What about the geometric multiplicity? Okay. So for 2, vector 0, okay, the vector 1, 0, what is the dimension of that subspace? 1. See, actually, if the algebraic multiplicity is 1, right, you don't even have to think. It's always 1. As long as the algebraic multiplicity is 1, the geometric multiplicity is guaranteed to be 1. Okay, okay, what about the next one? What is the next matrix?
1, 6.
Okay. Yeah. Here, there is only one eigenvalue. Is it plus or minus 1? Okay. What is the algebraic multiplicity? It's not plus or minus 1. It's not plus or minus 1. The equation is lambda minus 1 into lambda minus 1 equals 0. Lambda has to be 1. Yes. Yeah. What is the geometric multiplicity? I'm sorry. Algebraic multiplicity. I'm sorry. Yes. Algebraic multiplicity. No, here it's the number of times an eigenvalue is repeated. How many times is 2 repeated? 2, that's all. What about the geometric multiplicity? Right? X can be any vector from R2. So what is the dimension of this subspace? Eigenspace corresponding to the eigenvalue 1. R2. What is the dimension of R2? 2. Okay. What is the next one? This is the complex one, right? So the next one, that we won't do that. It's fine. That is also okay. The same thing applies. There are 2 different eigenvalues. Well, let's do that. It's fine. Right? This one, right? Okay. What are the eigenvalues? Yeah. I minus I, 1, 1, 1, 1. There's nothing to discuss. Okay. Okay. Let's do one example. Let's find the eigenvalues and eigenvectors of this matrix. Let's compute the eigenvalues first, and then tell me what the eigenvalues are. Oh, right. Yeah. The eigenvalues. Two and 1 is it? Hey, here I changed it. Sorry. Yeah. One and 3. Here. Yes. What is the algebraic multiplicity of 2 now? 2. It's repeated twice. Let's find the corresponding eigenvectors. What do you get? Yeah. Eigenvector cannot be 0. You've done a mistake. What is A minus 2i? This is what you're trying to solve, right? There is definitely a non-zero x that will give you this. Zero, 1. Okay. If you say 0, 1 now, you're taking 0 times the first column plus 1 times the second column. That's not 0, 0. Yes. You can verify this. The only vector, or okay, this will solve it. And any alpha times this will solve this. Okay. These are the only set of vectors that will solve it. Okay. What is the span of? Span of this? 1. That's the eigenspace associated with the eigenvalue 2. And what is its geometric multiplicity? This is 1. This does not match. Okay. This is a problematic matrix. Okay. We'll see what that problem is a little later. Okay. So in general, your geometric multiplicity is always less than or equal to algebraic multiplicity. And whenever it's less, you have problems. Those are the matrices for which you cannot find a full set of eigenvalues and eigenvectors. The eigenvector, sorry, the eigenvalue 2 is repeated twice. For good matrices, we should be able to find 2 linearly independent eigenvectors corresponding to 2. As many eigenvectors as its algebraic multiplicity. For defective matrices, you cannot find sufficient number of eigenvectors. So your GM is less than A. Okay. Okay. All right. With this in mind, we'll move to that. Okay. So now, let's say we are going to be only working with working with matrices that have a full set of eigenvalues and eigenvectors. Okay. That means matrices for which for all the eigenvalues, the algebraic multiplicity and the geometric multiplicity are equal. Let's say we have a matrix like that. Okay. And its eigenpairs are given by this. Lambda I xi. Okay. Lambda I could be repeated. If it's repeated, we have enough number of linearly independent eigenvectors. So this is still okay. Right? AM is equal to GM for all eigenvalues and eigenvectors. Sorry, for all eigenvalues. Okay? So if these are eigenpairs of my matrix A, right, then I can write this, right? A1 x1 will be what? Lambda 1 x1. And I know so not A1 x1, AX1. AX2 will be lambda 2 x2. Okay. Now, if I take all my eigenvectors, right, and say I stick them into a block row like this, what will be the dimension of this matrix, or what will be the shape of this matrix? Yeah, n cross n. Good. Okay. Okay. Now, if I pre-multiply by A, what will I get on the? If I multiply this, what will happen? If I take the product of these two matrices, what is the first column of the resulting product? No, I'm asking about the first column of the product. Since I'm asking about the first column of the product, use the column view. What is the first column of this product? Of what? Oh, it has to be the other way around now that I've disagreed with you. It will simply be AX1, linear combination of the columns of A with the mixture coming from the first column of this matrix. I'm going to call this matrix capital X. Okay. Or with the second one. x2. But we know what these are, right? Since the xi's are eigenvectors, this is not this complicated form. It has a simpler form. Right? I can write it like this. See, because we've defined lambda I and xi to be eigenpairs. So a times x1 has to be lambda 1 x1. A times x2 has to be lambda 2 x2. Okay. Now, let's say I want to form a new I want to define a new matrix capital lambda. Okay. And I want to define it. I want to define it as a diagonal matrix. Okay. Whose diagonal elements are simply your eigenvalues. Because this is all 0. Okay. If that is the case, this whole thing, would it be x times lambda or lambda times x, or can I not write this as a product of x and lambda at all? You tell me. The question is clear. X is simply this matrix whose columns are the eigenvectors. Lambda is this diagonal matrix whose diagonal elements are the eigenvalues. If I multiply A by the matrix of eigenvectors, I get lambda 1 times x1, lambda 2 times x2 as my columns of that product. Can I write this matrix as x times lambda or lambda times x, or no? Or none, both of these are not possible.
They are a diagonal element to be represented as a standard basis instead of x.
Sorry, what are you saying? I don't understand. Not a diagonal element, diagonal matrix. Yes.
Follows the matrix
Which matrix?
lambda standard basis for E1, E2.
Okay. Then
Then capital lambda into like E1, E2.
hey, hold on. What is this matrix E1? What is this matrix?
I'm just saying that we represent the capital lambda matrix as an since this is an diagonal,
Yes.
so we represent as a standard basis for E1, E2.
Okay. Yeah. So after this, what? That is this capital lambda. Okay, fine. So we use this. What do we do after that? That's not the question, right? The question is you have a matrix like this. Lambda. Yes.
Identity frequency. So that when the lambda gets multiplied with it, we get the.
Hey, hold on. Guys, hold on. Maybe the question, maybe you've not understood the question. Please listen to the question very carefully. I have this matrix. Okay, forget about everything else. I have this matrix. The first column is lambda 1 times x1. The second column is lambda 2 times x2. The nth column is lambda n times xn. Okay, I have defined two other matrices. Capital X, maybe I write it down. I have two other matrices. Capital X is x1, x2, xn. And then I have my lambda matrix as simply lambda 1, lambda 2. This is all 0. This is also n cross n. Okay. I'm asking you, is this equal to lambda times x? Is it equal to x times lambda? Or is it not equal to either of these? Is the question clear? I'm asking you, can I represent this matrix as a product of x and lambda? Because in matrices, the order of the product matters. I'm asking you, is it lambda x or is it x lambda or none? Neither of the two. Okay, verify it and tell me. Don't ask me. Verify it and tell me. No, verify it and tell me. Fantastic. Just verify. Beautiful. You know the answer, verified. No, no, verified. It's fine. See, if you just show me that it's the same, right, then you've convinced me. They're the same?
Let me take an example on blue cross 2.
Hey, hold on. X is a vector. Is it?
It is a column.
Hold on. Okay. I will just write down what you've written, right? You've written lambda 1, 0, 0, lambda 2. And you've defined x1 to be x2. So you've said x times x1 is something. And then you've written x1 times. Is this operation even allowed? A 2 cross 1 multiplied by 2 cross 2. Okay. These sorts of mistakes you should not be doing. And here, guys, this is an n cross n matrix. Each one is a column. Again, if it's too abstract, right? Take a 2 by 2 example. Take any example for a matrix X and verify. Lambda 1, 0, 0, lambda 2. And take this one. X11, X12, X for X12, X21, X22. And let's call this your X and call this your lambda. See, see, this course is not about you remembering stuff. This course is really about you learning to figure out when you're in a situation where you have no idea what is going on, right? So whenever you see something, I'm asking you something and you have no clue what that means, simplify the problem, go to a 2 by 2 case, work that out, and then see if you can generalize to the n by n case, right? If you take anything from this course, please take that. Being able to simplify the problem, uh, breaking it into pieces that you can handle or you're confident about handling it, and then generalizing it, right? Yeah. So tell me what this is. The problem comes when you try to just remember. Sorry. Yeah. Yeah, you have it. What is it?
Lambda 1 is mapped to all the first.
No. Okay, you don't have to explain all of that. You tell me which of these is true, assuming for this matrix. See, in fact, uh, the product that we want to have is this lambda 1, this, lambda 2 times this. So that means what we want to have is lambda 1 x11, lambda 1 x21, lambda 2 x12, x22. Yes. Okay. Now that it's x lambda, you verified with this or the general case. Okay. How did you? Why is it? Why is it x lambda? Good. Okay. You use the column view. How did you use the column view? Or why did you have to use the column view?
Lambda
Okay. So you use the inner product, but it looked like x lambda was yes. Okay. Here you have a matrix x1, x2, xn. You have to multiply it by another matrix to get lambda 1 x1, lambda 2 x2, lambda n xn. That means you want the first column of your product matrix to be a linear combination of the, well, each of these columns is a linear combination of the columns of x. So x has to come in front, because only when you post multiply by something are you taking the linear combination of the matrix in the first matrix. Right? So this is in fact x lambda. If that is still confusing, here, if you do x lambda, what is the first column of x lambda? Forget about this. What is the first column of x lambda?
X.
Yes. X1, no, x. What do you mean by x1? X, the matrix x, no? Hey, no, hold on. If I do x lambda, what can you say about the first column of this product? Yes. Linear combination of columns of x. Oh, okay. It's columns of x. I cannot go back now. Fine. Okay. You can verify here. The first column of this product is the linear combination of the columns of x with the mixture coming from the first column of lambda. The first column of lambda has all 0 elements except for the first one. That means the resulting product for the first column will only include x1. So it will be lambda 1 x1. Now the second column will be linear combination of these with the second column of lambda. Everything is 0 except for the second element. That means the only thing that remains is your second column of x, and that's why you get this. Okay? Correct. So what you end up having is A times this matrix x is in fact equal to x times lambda, and this is simply a restatement of this. Okay, I've written it as individual n equations here. The matrix representation is essentially this. Right? Now, since we've assumed that we have a full set of eigenvalues and eigen vectors, and what that means when I say I have a full set of eigenpairs, what I really mean is my xi's are linearly independent. Okay. I can find n linearly independent eigenvectors for all my eigenvalues, irrespective of whether they repeat or not. That's what I mean by I have a full set of eigenpairs. Okay. If I have a full set of eigenpairs and my xi's are linearly independent, then what can you say about the rank of the matrix X? 10. Yeah, it's full rank matrix. If the rank is n and it's square, that means X inverse exists. And let's say I want to move X to this side. How do I move it? Okay, I want to move X to this side. If I move it, what will I get? So I have A, I'll get X lambda X inverse. Why not X inverse X lambda? Yes. If you say, if you will get X inverse X lambda only if you multiply X inverse here. That means you multiply X inverse to the left side. So what you get is this, right? Right. This is your or third matrix decomposition. Third of the matrix decompositions. So this is the eigenvalue, or maybe eigen decomposition. I can't remember the name. Eigen decomposition of a matrix A. We've seen two other, right? What are the other ones we saw? The matrix decomposition methods. We saw the QR and then LU. Okay, and now we have the X lambda X inverse. Okay, what are the columns of X? When you write it like this, what are the columns of X? Where lambda is a diagonal matrix. Yeah, the columns of X are the eigenvectors of your matrix A, and the diagonal elements of your lambda are your eigenvalues. Okay, but we've seen something like this earlier, no? No. This module, we started this module not by discussing eigenvalue, eigenvectors. We started discussing something else. Similarity transformation, right? Or the idea of similar matrices. What is the idea of similar matrices? If I say A and B are similar matrices, what do I mean? What do I mean by that? When I say A and B are similar matrices? Hey, that simply means A equals B. You're saying the elements are the same, that means A equals B. No, what did we discuss? Go back. Sorry? Sign, is it? Hey, signs all. We can talk about similar matrices only for square matrices. Yes. See, in fact, okay, I'll agree with you. They have to be of the same size, yes. But what does it mean to say similar matrices? No, okay. Similar matrix simply means that both of them represent the same geometric operation, geometric linear operation, or linear geometric operation, whatever that is, operation, but in different bases. And in fact, if that is the case, then A and B can be written like this, or P is X inverse A X. Okay, and because I've written X inverse, that means these are invertible matrices, which they will be because X simply represents the basis in which B represents A. Okay. By that argument, what can you say about A and lambda? Are they similar matrices? Yes, they are, right? They are of this form, right? So in fact, A and lambda are similar matrices. Okay, and lambda is simply the representation of the linear transformation represented by the matrix A in the eigenbasis. Okay, and what I mean by eigenbasis is I define my basis to be, so the eigenbasis is simply the set. Eigenbasis is simply the set of eigenvectors. Okay, this is the basis for Rn because we started by assuming that we are dealing with only matrices that have a full set of eigenpairs. That means all the xi's are linearly independent. And because any n cross n matrix has n eigenvalues, there should be n eigenvectors. So there is a set of n vectors here which are linearly independent, which means this has to be a basis for Rn because the span of n linearly independent vectors from Rn is Rn. Okay, so this forms a basis. So your A and lambda are simply similar matrices, and if A represents a linear transformation in the standard basis, then your lambda represents the same geometric operation but in the eigenbasis. Or another way people think about this is we have some geometric operation that A represents, right? Right? That's the geometric operation A does on any vector that you give it. Right? And because A has a whole bunch of numbers, it's really hard for us to make sense of this matrix, okay, as to what it's doing. Okay. But instead of, so this is A in the standard basis, right? But instead of this representation, if you ask what does the matrix look like in the eigenbasis, what you get is this. It has an extremely simple representation. Okay, you only have n number that you have to worry about. And in fact, it's very clear what this matrix is doing. It's simply scaling each of your or scaling components of vectors along each of the eigenvectors. Okay, so this eigen decomposition is often thought of as a process of simplifying a matrix because you're diagonalizing it. Or another way to think about this is if A is this, then I can write lambda equals what in terms of A? What will it be? If A is x lambda x inverse, this will be x inverse, right? If you have a complicated looking matrix with lots of numbers in like this, if you have the eigenvalue decomposition, you can obtain a simpler representation of your matrix A by simply doing the similarity transformation. Okay. Okay. Now we'll go back and we will write down all the matrices for which we found eigenvalue and eigenvectors in this form. What is the first matrix we looked at? Yeah. First one is what? 2, 2, 1, 1, 2 or 2, 1. Okay. Now tell me what is the corresponding eigenvalue decomposition for this matrix? I know what will go in the middle, right? What will go in the middle? What is it? I know what will go here, right? This also you found out. What is it? You have it? One, 1, 1 minus 1. Is that correct? Now we'll have to find out this. How will we find this out? Are you sure? You have to find the inverse of this. Okay, minus 1, is it? Just verify it and tell me before I write it down that it is in fact the inverse. You can verify this. This will simply be 1 by 2. You can multiply this out and you can verify this is in fact true. Okay, it's okay. What about the next one? What is the next matrix? Was it 2, 0, 0, 1? Is it this? Yeah, okay. What are the what about here? What are the eigenvectors? And what is the inverse of this? Yes, inverse of I is I. But this is I multiplied by lambda multiplied by I. What is that equal to? It is equal to lambda. Well, it's kind of silly. You already started with the simplest possible representation of the matrix, right? So obviously, because the eigenbasis is the standard basis itself, these are the basis vectors. The basis vectors are the standard basis. So this matrix has no other, you cannot simplify it anymore. This is the simplest possible representation. So this is in fact equal to just. Okay. What about the next one? Here it's slightly different though, or maybe it's so 1, 0, 0, 1. What are the eigenvalues? Oh, sorry. What are the eigenvectors? Huh? Yes. Okay. Here is the thing you have to be very careful about. You can choose anything from R2, right? So I can choose 1, 1. That is okay. I can choose a second eigenvector also to be 1, 1. But that's a problem. That forms a linearly dependent set, right? So when you have geometric multiplicity that is greater than 1, what that means is you can choose, let's say, for example, here the geometric multiplicity is 2, right? It simply means if the algebraic multiplicity equals the geometric multiplicity, it simply means you can choose uh, enough number of linearly independent eigenvectors from the eigenspace, right? Because the eigenvalue is repeated. The geometric multiplicity of my eigenspace associated with 1 is 2. That means I can choose two vectors from that eigenspace which are linearly independent. And if I stick two linearly independent vectors here, let's say 1, 2, 4, 1, and if I simply find the inverse of that, this is perfectly fine. Okay, so whenever you have repeated eigenvalues and am equals gm, you can always find as many required linearly independent eigenvectors as you need. Okay, and in fact, this is I, that means this is simply this inverse that multiplied by is I. So in fact, it's stupid. You started with I again. This is got the simplest possible representation, right? And because the entire, I mean, anything can be the eigen basis for this as long as they are linearly independent. I could have written it like this. This already has the simplest possible representation, so it's actually equal. You cannot simplify it further. Okay, all right. We'll discuss one more idea about this process of simplifying stuff. Then we'll move on. Okay. Okay, let's assume we have an ellipse. Okay, in R2. Do you remember the equation for an ellipse like this? This is x1. This is x2. Yes. So it's of this form: x1 square by a1 square plus x2 square plus a2 square is 1. That's a very nice simple representation. Okay. What about an ellipse like this? Let's say it's centered around 0. Do you remember what the representation is? The algebraic equation for that? Do you remember? No, that's okay. 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 Let's say we take, so this will be of this form. Some a x1 square plus b x2 square plus c x1 x2 will be 1. Okay. It does represent this ellipse if you choose a, b and c appropriately. Okay. And you would argue that clearly that is a simpler representation than this. Okay. All right. Now let's take an example of one such ellipse. Okay. It turns out whenever you have an ellipse equation like this, right, you can actually write this as in a matrix form. Okay. You tell me what that form will be. I'm going to define a vector x as x1, x2, and I'm going to define a matrix A, okay, elements A, B, C, D. Yeah, A, B, C, D. It's fine. And I'm going to claim that if you choose the elements of A matrix carefully, then I'm claiming that this is in fact equal to this. Okay. Now tell me what will be the values of A, B, C, D so that this is equal to this. Again, a simple practice of multiplying matrices and vectors together. First of all, before you even do the multiplication, the right hand side is a scalar. Does this give me a scalar? Okay. So, okay. X. What is an inner product? Where is an inner product here? Inner product involves two vectors, right? A row vector and a column vector. So okay, X transpose.
That was in that.
Yes. Yes. Perfect. Yeah. Or you could have argued it other way. This is 1 cross n. A matrix post multiplied by a column gives me a column. You have a row and a column. So this is okay. So at least in terms of dimensions, this is correct. Now tell me what, if you multiply this out, what is the expression you get? And then from that, can we figure out what A, B, C, D are so that we get this equation for this ellipse in this format? What do you get if you multiply this out? Okay, tell me the expression for this first. Okay, ax1 square let's do one simplification. Let's keep it b. Okay, so then it'll be okay. Okay, now tell me what is a. What is a? You had it, no? 3, 3. Yeah, -1. Why are you so concerned? It's 2 times b. It's -2, so it's -1. That's fine. So if you take x transpose ax, you'll get that equation. Okay. Now find the eigenvalues and eigenvectors of this matrix. You'll get it. You'll get it. What will change is instead of the equation being written in terms of x1, x2, it will be written in terms of v1, v2, where you're simply changing the bases. And the bases are the axes along the major axis and the minor axis.
Proper roots is the numbers. You won't be like
I think you get 5 and 1 or something like that. Let me check. Yeah, 5 and 1. Yes. Or 4 and 2. 4 and 2. Yeah, you guys got it? What are the eigenvalues? Great, that's correct. 4 and 2. Okay, so you have lambda 1 equals 4, lambda 2 equals 2. Tell me the corresponding eigenvectors. You have it? It's okay. It's all right. What is it? Tell me. Yes, that's all. So tell me in terms of numbers. Let's not do alpha. For 4, 1, 1, 1, 1. Yeah. Okay. Okay. And here? Ah, yeah. Okay. Now tell me what is your eigenvalue decomposition of this matrix. And okay, let's write it down like that first. What is the eigenvalue decomposition of this matrix now? What is x? What is lambda? And what is x inverse? In fact, I'll just write it as inverse for now. What is x? I mean, you're right. Tell me. Yeah, 1. Okay, 1, 1. That's okay. If this is an eigenvector, minus 1, 1 is also an eigenvector. So that's okay. Okay, and so this will be 1 minus 1, 1, 1. And here? Yeah, 4, 0, 0, 2. What is the inverse of this matrix? X. Tell me what the inverse is. I'll actually replace this. Let's write the actual inverse. Yes, 1 by 2. 1 half. Minus 1. What is this element? Is it 1? No. Okay. What is it? 1, 1, minus 1, 1. Okay. Here. Are the two eigenvectors orthogonal to each other? In this case, they are, right? And one thing we can do is, let's say we normalize the eigenvector, right? We don't make it, we ensure that the eigenvector is of length 1. Okay, so I will have to multiply this by, okay. Now, these two are orthogonal to each other. They're of length 1. That means they form an orthonormal basis. So if I form a matrix X with those eigenvectors, the matrix would be an orthogonal matrix, right? Okay. If I have an orthogonal matrix, what is the inverse? The inverse of an orthogonal matrix is its transpose. So this will simply be 1, 1 minus 1, 1. Okay. So in fact, my A now is simply X multiplied by this X transpose. Okay, where X is 1 by root 2, 1 minus 1, 1, 1. Okay, in this case, it just turned out to be nicely, it turned out to be very nice that the eigenvectors came out to be orthogonal to each other. Okay, right. So we know that that oblique ellipse can be written down as X transpose. Maybe I'll do one thing. I won't call it X. I should have done this earlier also. In the notes, I have it as V. So we know the ellipse is equation for the ellipse is written like this: the vector X transpose A 1, right? But we know A has this representation in the eigenbasis, right? Or the the eigenvalue decomposition of this matrix is this. Okay, so I can write it as X transpose V lambda V transpose, right? I've simply replaced A by this. That's all. I've not done anything else. Okay. Now, if I take the parenthesis out, right, I'll take this out, right? And let's say I combine these two together. Okay. And let me say I call this V. I call capital V transpose X to be, let's say, Y, not V. Okay. Then what is this? This is Y is equal to 1. Yeah, you're right. What is it? Y transpose. If you take the transpose of this will be the transpose of the whole thing. Reverse the order, take the individual transposes. It will be X transpose, V transpose, transpose. This is V. Okay. Let's say Y is Y1, Y2. What is the equation of this ellipse? Or what is, I will not call it an ellipse. What is this equation work out to be? In fact, lambda is 4, 2. So in fact, I'll remove that and write. But tell me, what does this work out to? This thing worked out to be this, right? What does this work out to? No, what is this? What is the equation that you get if you multiply this out? Yeah, you have it? Yes, yeah. Okay. This is an equation for an ellipse. And we obtain this from where? This was obtained from this is what we started with, right? We started with this. We made a representation for this in terms of this A matrix, found out the eigenvalue decomposition of A, and then when you then inserted that into this equation, you started with this equation and ended up with this. They are not the same equation, right? Because the variables are different. This is in terms of x1, x2. That's this. That's this. This is x1. This is x2, right? But this one is in terms of some other variable, y1, y2. We don't know what that is yet. Okay, but this is definitely simpler. Okay, now this ellipse looks oblique. Okay, because I've drawn this as my coordinate axis, right? I've said this is my x1 axis, this is my x2 axis. If these two are my coordinate axis. Of course, this is oblique. But you could come and say, well, what if I choose my x basis to be like this? For somebody who's working in the blue basis, they say this is a very simple ellipse. It's not oblique at all, right? And in fact, that is what those two equations tell you, right? Yes, it's simply a change of basis, right? An ellipse with a complex formula in the standard basis simplifies to that when you move to the eigenbasis. And in fact, the two basis vectors that you found are simply the two axes of this two-dimensional ellipse, right? This will be your y1, y2. Okay. So that's one of the uses of eigenvalue decomposition, where complex things tend to look simpler if you simply change your point of view. Point of view here being simply what basis do you use. Right, okay. Now, this kind of nicely leads us to the next topic. This particular matrix now ended up having orthogonal eigenvectors. In fact, that is a general trend for a special group of matrices, especially symmetric matrices. This is a symmetric matrix. What is a symmetric matrix? Hey, hold on. No. Yes, that's all. A transpose equals A. You can verify that A transpose is equal to A there, right? So, in fact, when it comes to eigenvalue decomposition or eigen decomposition of matrices, symmetric matrices are very special. Okay. Symmetric matrices, okay, where A transpose equals A. Okay. It turns out symmetric matrices are always uh, will always have an eigenvalue decomposition. Okay. Always have eigen decomposition. Okay. That means we can always find a full set of eigenvectors for symmetric matrices. Two, the eigenvalues will always be real. You can have repeated eigenvalues and all that, but the eigenvalues will always be real. And three, the eigenvectors can be chosen to be orthogonal. Okay. The reason we say they can be chosen to be orthogonal is when you have repeated eigenvalues and you have let's say eigenvalues repeated twice, right? And you have a two-dimensional eigenspace, right? We choose any two vectors from that eigenspace, right? Those are valid eigenvectors. Because it's two-dimensional, you can choose to get two eigenvectors which are orthogonal to each other. Okay, that's what it means to say can be chosen to be orthogonal. Of course, if the eigenvalues are distinct, right, then the eigenvectors will be orthogonal. For example, 4 and 2, the eigenvectors were orthogonal. If you go back to one of our previous examples, is this a symmetric matrix? This is a symmetric matrix, right? How many? What are the eigenvalues? 2. It's 2. It's repeated twice. And what is the eigenspace associated with the eigenvalue 2? What is the eigenspace associated with the eigenvalue 2 of this matrix? Hey, hold on. Yes, it's all of R2, right? Because it's all of R2, I can choose two vectors from there which are orthogonal to each other, right? So I can choose 1, 0, 0, 1, which is orthogonal, or that one, 1, 1, minus 1, 1, scaled or normalized by 1 by root or something like that. Right? That's what I mean by they can be chosen. Okay, if eigenvalues are repeated, you don't have to choose, but choosing orthogonal eigenvectors is nice because then X inverse is simply X transpose. All right, fine. This is all I want to say. For matrices that cannot be diagonalized, okay, for which AM is greater than GM, you cannot express it like this. That means you cannot simplify the matrix to look like a diagonal matrix simply by changing a basis. Okay, and for matrices like that, you cannot diagonalize, but you can get it to something close to a diagonal form. So if A has a full set of eigenvectors, then you can write it like this. Sorry. V inverse. When your matrix is defective, that means your AM is greater than GM for some eigenvalues, then this is not possible anymore. Okay, you cannot get a diagonal matrix. What you can get is what is called the Jordan form. I will not discuss this at all. Okay. What you can do is write this form. This is called I think the Jordan matrix. I could be wrong. I can't remember, but it's in the notes. You can in the slides you can verify. I don't know what the name of this matrix is. J is not quite diagonal, but it's almost diagonal in the sense that, for example, you remember one of the problems that we did now. Okay, the eigenvalues were 2. There was only one set of eigenvectors. Okay, this is the Jordan form. The eigenvalue is 2. It's repeated twice. So ideally, what I should have if I simplify the matrix is this diagonal multiplied by V inverse, right? But when you don't have a full set of eigenvectors, and let's say you have two eigenvalues 2, and it's repeated twice, you cannot get a diagonal version. What you can get is something like this. There will be a 1 in the super diagonal. Okay, and how many ones you have, it depends on the difference between the algebraic multiplicity and the geometric multiplicity. We don't have to worry about those things in this course. Right? So I will just stop here. If you simply remember that there are the matrices for which you cannot get the diagonal, which you cannot diagonalize, and the best you can do is the Jordan. Okay, all right. That's all I wanted to say about this module. We'll do the tutorial tomorrow. See, what I want you to do is please go and revise the material from today's class for next day's class. Right? For example, I expected you guys to already know similarity transformation, at least be able to recall it. Okay. Right. So revise this for the tutorial session tomorrow. Yeah. All right. Thanks.